I'm really excited to talk to you all today. So I guess I normally do pure mathematics, which is less about applications, but today I want to talk about some applied work that I have done. So I went to college to learn how to build electronic music instruments, and then after learning that, I couldn't find a job making electronic music instruments. So I ended up looking into mathematics and found out that I like mathematics more than wiring together circuits. So when I started doing mathematics, I came at it from a very applied angle. So I initially did research on mobile robot vision. So we were working specifically with robots that had very high level of vision software for, this was 20 years ago. Um, so mobile robots with facial recognition software. So we could use that to like recognize a tree and then look away and then come back and realize that it was the same tree, even if we're looking at it from a different angle. Uh, then later, I started working on groups of mobile robots, and that's what I'll be talking about with you primarily tonight. Sorry, today. I guess it's daytime where you are. Um, but as things go forward, feel free to ask me questions, and I'll be very forthcoming about what I do and don't know, or I'll at least tell you what was the state of the art when I was working on it. Um, but yeah, so with that, let's get into what I've titled Field Reconstruction via Sensor Swarms. And hopefully by the end of the talk, you'll have an idea what each of these words mean. So this was joint work with Josh Kirby, Marco Montes de Oca, Lou Rossi, and Chin-Chung Shen. So, oh dear, let's see if can I do this? Yeah. So basically, the plan for this talk is I want to give you some background for what are the individual pieces of the title, and then I want to show you sort of the work we did, and this would have been 2013, 2014 when I was working on this particular project. So I'm going to try to give you a wide base of background, then describe the individual pieces that we're going to work with, and then I'll show you the particular data or some of the data that we got, so the specific results for how we approached and solved this problem. So uh, here are some just types of things that I might want to know as a human. So forest fires. So forest fires are a big problem. If someone wants to fight a forest fire, they need to know where to direct their resources, right? So you have various, sources of water or other ways of slowing down the fire, and you might want to know where the fire is burning the hottest or where the fire is maybe cooling down, but you probably don't want to send people in there to find it out. Oil spills. This is another big problem. So there's an oil spill in the ocean. A tanker falls over, and now there's oil leaking everywhere. And we want to know, where is the oil most concentrated, or where does it just sort of look like there's oil? How do we clean up this mess most efficiently? And another example is nuclear waste. There have been numerous nuclear disasters where there's nuclear waste everywhere, and again, you probably don't want to just walk through the nuclear waste field. So I've called all of these danger zones because these are places where I want to know what's going on, but I personally don't want to bring my body into that situation. So these are some tasks that I might want to do with robots, in particular, groups of robots. So some other things that robots are used for, maybe just that you might not think about. So healthcare, people are starting to send robots inside of our bodies that can either deliver medicine or fight cancer. Construction, there are robots now that do things like, I actually just saw on the news yesterday, apparently Japan has a giant robot for maintaining the railroad tracks. But there are robots that do things like lay bricks. And if you get a bunch of these together, then you can do a lot of construction quickly. And finally, most important, aerial light displays. So yesterday here was the day that we shoot off the fireworks, and the whole sky was lit up with fireworks. But that's, of course, maybe not so good for the environment to burn a bunch of stuff. So a new recent trend is for people to send up drones, and the drones have lights on them, and then they have the drones fly around, and you get an animated light show that's maybe not so smoky. Although actually last night there was also a thunderstorm, so it was really pretty. There was lightning over here, fireworks over there. It was a fun night. My dogs were not too happy. Okay, so what am I talking about? I'm talking about a swarm of mobile robots. So not just one mobile robot, but many simple autonomous mobile robots. For me, that's when I say the word swarm, at least in today's context, I mean a large group of autonomous mobile robots. Okay, what's a robot? I'm typically thinking of some sort of electronic device, and it's going to somehow interact with the physical world. So it's not like a Raspberry Pi that sort of sits there and blinks. I'm thinking of something that either can, lift objects or, actuate, do something in the real world. What is a mobile robot? It's a robot that can move around. So we can think about, cars that autonomous cars that drive around on the roads. We can think about the drones, the quadcopters that can fly around, or we can think about underwater robots. So they have robots that can swim through the ocean. Now, what's the word autonomous mean? Autonomous here means it controls itself. So you can imagine somebody sitting far away with a remote control and sort of controlling the robot like a video game. When I'm talking about an autonomous robot, I mean a robot that can essentially control itself. Humans will tell it what to do at some high level, but there's maybe not a human actually controlling it like a video game. Now, these other words, many simple autonomous mobile robots. So when I say many, with a swarm, I'm typically thinking about not just 3 or 4, but maybe dozens or even hundreds of these robots. And if I have so many robots, it's probably going to be pretty expensive for me to have all of them being super, super complex and super complicated and super expensive, right? So we typically want many simple autonomous robots. Is a plane on yeah, you could think of a plane on autopilot as an autonomous robot. And if you can imagine a whole bunch of planes, you could think of that as a swarm. And again, here I'm thinking of this as a general concept and less of like this is a swarm, that's not a swarm. But this word swarm we use to describe like a group of bees, like the many bees fly around. We call that a swarm of bees. There are lots of different groups of animals, like a school of fish or a flock of birds. But all of these we're going to call generally a swarm of animals. And so now we're looking at a swarm of autonomous robots. So we're taking a lot of our motivation, a lot of the ideas come from nature. So this is a strange phrase here. What I'm saying is we want emergent behavior. So what is emergent behavior? Remember, I told you this is a whole bunch of simple robots, and you can think about like a whole bunch or very many simple things. We want somehow all of them acting together to do something big. So I want you to think like how a small ant can't do that much on its own, but if you have hundreds of ants together, they can build an impressive ant hill, which behaves like its own sort of superorganism. So when we say emergent behavior, and this is a common phrase you'll see if you read up on swarms, what we mean is a simple set of rules for each of the individual agents or each of the individual robots that somehow when we put those simple rules together, they make a big, complicated, impressive structure or some big, complicated display. And now I mentioned this, but I want to really hit on this. Remote control is often not feasible for a number of reasons here. So when I have, hundreds or thousands of robots, I probably can't pay 100 or 1,000 people to pilot each of them. So when I'm thinking of swarms, I'm thinking of a case where I don't have people to control them. I have too many robots. The situation is too complicated, or the reaction time. You imagine a whole bunch of things flying in a formation like this. the reaction time is too fast and humans are just not going to be able to do it. Another reason we might have this is if we're in some sort of noisy or lossy medium. So if these are robots that are far, far, far underwater, or if they've gone into some, far reaches of space or wherever it is that we just don't have regular, quick communication with them. So oftentimes we'll send a swarm, or we'll think of problems where we're sending a swarm somewhere that it might have to make decisions on its own, that aggregate group might have to make decisions on its own and then just send the data back to the humans. So is the idea of a swarm relatively clear? I know I'm making it fuzzy. It's not like this is a swarm and that's not, but this is a kind of thing that I'm talking about. Are we all right with that? Yeah, and again, at any time, feel free to stop me with a question and I will do the best I can to answer it. So so when I talk about swarming, what I want to do is I want to give you some simple rules, and I want those simple rules to have this emergent behavior. So the particular algorithm that I'm going to use as the foundation for this is 3-zone swarming. I'm going to describe these zones, so how they work, and then I want to show you some examples of how they would work in a simple type of swarm. So for 3-zone swarming, we're going to basically give these robots 3 different sets of rules. And this can work in 2 dimensions, this can work in 3 dimensions. But for the illustrations I'm going to give you, you can just think of these as sort of like remote controlled cars on the ground, or you can think of them as birds in the sky, but I'm just going to focus on the 2-dimensional behavior. So for 3-zone swarming, what I want to do first and foremost is I want to make sure that my robots stay alive, right? I mean, they're not alive like humans are alive, but I want to make sure that my robots keep moving and don't crash. So the highest priority is that agents are going to move away from each other if they get too close. So you can imagine if I have 2 sort of remote control or sort of robot cars moving at high speeds and they get close to each other, you want them to not run into each other and then stop working, right? So the most important thing, the highest priority, is that agents are going to move away from other agents that they are too close to. So I'm going to call this the zone of repulsion. Next, for agents that aren't too close, and when I say agent, I mean robot, but agents can also mean bees or birds or fish. So the word agent can apply to anything. But here when I'm saying agent, I mean robot for our purposes, but this 3-zone swarming model we'll see also applies to fish and birds and other things. Okay, so we want to make sure that they don't run into each other, that the quadcopters don't crash and then they blow up. Next, as long as they're not going to run into each other, if they're at sort of a medium distance, then the next priority down is that they align orientation. So what does orientation mean? It means that the robots are going to look to see where everyone else is pointed, which direction everyone else is heading in. So I think of this like a group of people walking across a street. You're walking across a street, and then you want to make sure that you're all kind of moving in the same direction. If people are walking across the street and they're all weaving this way and that, people can bump into each other. It can be confusing for drivers. So when we're not going to bump into each other, we're going to try to make sure that we're moving in roughly the same direction. We're all going to look at each other and try to like sort of head in the same direction. So finally, the 3rd zone. So there's the closest zone is with every robot, what's its immediate surroundings. Then there's some sort of middle ground, and then agents that are outside of the middle ground, so the lowest priority, is that we're also going to have some sort of desire to move towards agents that are far away. So this should make sense because I want my swarm to stay together. I want it to be one group and not just have everything flying all over the place, right? If I want to send my swarm into a region, maybe they can spread out a little bit, but I don't want them to just, oh, we're too close, and then all go to the 4 corners of the globe, right? That's not probably going to be so productive. So what really excites me about this is this orientation zone. So when I got into this project, I heard about zone of repulsion. I heard about zone of attraction. That made sense. Don't bump into each other, but also kind of stay in a group. But the zone of orientation I thought was really interesting. So just sort of at a meta level, for those of you who are maybe more into mathematics and less into engineering, more into pure math, I think of repulsion and attraction as doing with position. So these are position, whereas this is a velocity criterion. So I think that's interesting that we're moving the agents based on the positions of the other agents and the velocities of the other agents. Again, velocity is direction and speed. So it's not just how quickly these agents are moving, but also the directions they're moving in. And one note that is very important, and I don't know if I'll have time to come back to it, but the idea that robots might change their speed is very complicated. So I want you to think about if you're driving in traffic and cars are constantly hitting their brakes and then accelerating and hitting their brakes, it's very inefficient movement. So oftentimes swarming models will assume constant speed. Now, physical objects are probably not going to have constant speed, right? There's going to be wind blowing on the quadcopters. There are going to be currents pushing against swimming robots and what have you. But the idea that a robot can just stop and start again is actually kind of complicated. So we're going to pretend that our robots are always moving for most of this, and then later, in sort of the second part of the talk, we'll modify this to where robots can start and stop, and you'll sort of see why that becomes something later. So do we understand that the idea of the three zones, there's close, there's far away, and then there's whatever's in between? Okay, so here's sort of a diagram. So this agent in the middle, this is pointing up. So I'm really looking at this central agent. Each one of these little V's is, I'm thinking of these as robots that are pointing in different directions. Moreover, I'm actually thinking about these as moving. Remember, these are mobile robots, but we've just taken a picture of it at a point in time. So what's this agent thinking? Well, this agent is thinking, here is my zone of repulsion. Here is my zone of orientation, the yellow, and then outside, the far away, is my zone of attraction. So what's the highest priority for this robot? The highest priority for this robot isn't to meet up with his friends that are far away, and it's not to look like his friends that are nearby. His highest priority is to not bump into this person that's very, very close to him. So that's why we have this robot oriented up and this robot oriented down. They don't want to bump into each other. Now, as long as they're not going to bump into each other, this robot should be, like if this one isn't here, let's look in the zone of orientation. Let's look in this yellow area. We see that maybe they're pointing in slightly different directions, but the overall average direction is upward, right? So this one's kind of up, this one's kind of up, 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 kind of down. But if this robot wasn't here, we'd still probably be pointing upwards. Okay, now, if the yellow robots and the red robots weren't there, then we'd probably be pointing down because there are 5 robots on the bottom and only 4 robots on the top. Right? So do you see the loose idea? Now, since each of these are moving, each of these robots is constantly reevaluating, should I keep going in this direction? Oh, should I turn? Should I spin around? What should I do? So to get you all sort of thinking like this, I set up a few examples. So I'm going to show you 3 zones. So there's going to be a robot in the middle, and then I want you to try to guess, which way this robot should point. Okay, so here the question mark is the location of a robot. So I want you to take a second and just think about, or you can say in the chat if you want, sort of which direction should this robot point? And I'll just give you a second to think about it, or you can unmute and say it. That's fine too. Okay, yeah. So we've got Dao said up. Yeah. I agree. I think this robot's going to point up. So why should it point up? Well, doesn't it want to be close to these friends and in the zone of attraction? I mean, it would like to, but there are all of these robots here in the zone of repulsion. So this is a pretty easy up, right? It's clear that this robot doesn't want to run into these other robots, so it's going to definitely need to point up. Okay, another example. So just say loosely what you think, and if you want to, say why. Say roughly which direction it should point and why it should point in that direction. Okay, so we got somebody saying to the left. Yeah. So Le is saying that it should go to the left. And yeah, that's right. This one should be going to the left. And why should it point to the left? Again, let's look at the robots that are in its area of orientation. So there's nobody in the area of repulsion. So we can ignore, running away from anyone. But now our next highest priority in this zone of orientation, there's one robot pointing to the right, but everybody else is pointing essentially to the left. So we want to essentially be pointing leftwards. Okay. So now I think this one's also fairly straightforward. Which direction should it point? So again, there's nobody in the zone of repulsion, nobody in the zone of orientation. So it's going to be pointing, down, down, and southwest is also correct. Yeah, down and left, downish, leftish, southwest, south by southwest. That's all correct. Because again, it wants to point towards where there are the most of these robots. So presumably some of you have had how many of you have had vectors? How many of you have seen vectors in school so far? You can do like hands up or something like that. How would you imagine either writing a mathematical expression or a computer code that would tell you what direction precisely this robot should point in? You can just describe it like, oh, here's what I would do, or so I guess what I'm asking is, if I'm thinking of computer code, right? How do I write computer code that's going to get down and left from this? Because there are some vectors pointing up and right? If I'm looking at the direction from this to here, but then there's this, how do I make sure that it ends up sort of coming down here? Can anyone come up with an idea? Okay, yeah, taking the majority. So that's definitely a very good idea, Tang. So yeah, you could go with the majority. That's one way to do it. The way we typically do this, which is going to work out to be very similar, is we compute the distance from every single agent to every other agent, which is computationally very expensive, and we add those direction vectors up. So you can imagine this direction vector being a positive number paired with a positive. This is a positive with a positive. This is a negative with a positive. And these are negatives paired with negatives, right? And positive paired with very negative. So you add all those up and you're going to get some resultant vector. This is just like if you've taken a physics class and you've done a free body diagram. This is just like those resultant vectors that come from like different forces pulling on a body. Maybe you've seen like two people push a box in different directions. And so the box goes in kind of this average of their directions. So we're going to average this. So we're going to sum these, and typically we're going to take an average. So we're going to divide by the number of agents to get sort of a reasonable goal in mind. Okay. So now what I've got, another example, and this one I'm just going to sort of iterate this through. I've got a very small swarm. So this is just so that we can sort of wrap our heads around it. And I want you to think about what are each of these four agents going to do next. So let's, for the moment, pretend they have to move, and we're going to assume a relatively constant speed. I have done computer simulations and visualizations with this, but to keep this simple, I just sort of did these in a graphics program. So these are not super precise. But I want you to imagine, what are each of these four agents going to do? So what you might want to do is sort of pick one and imagine where it goes next. And if you can sort out where all four are going next, that's great. But I want to just iterate several steps. And so I'd like for you to imagine, like, sort of pick your favorite robot and guess where that robot's going to go. And take it just a couple of seconds and try to think about that. Okay, so let's see what happens. So these two were so close that this one had to go down. This one had to run away from this one. And this one's already running away. We look at this one, and these two are in its zone of orientation. So it's like, oh, well, from here it says, oh, they're both pointing up. I guess I should point up. Now this one has nobody in his zone of repulsion or his zone of orientation. So he's just attracted to the group. So he's going to come this way, and that's what we see here. Okay, now, oh, I guess this one didn't move. This one should have moved. Okay, now these two are kind of in agreement. They're far enough apart that they're not in each other's zone of repulsion. They're moving in the same direction, so they're pretty happy. This one now has one agent in its zone of orientation, two agents in its zone of attraction, and this agent is now no longer in a zone of repulsion, and it's thinking, ooh, I need to align myself, with the people in my zone of orientation. So this is loosely what's happening. And as we step forward, we see they kind of coalesce into one group, and that group starts to do what we call translation. So when I'm using a swarming algorithm, I'm typically mimicking things that swarms do in nature. So a swarm might translate, which means it's in roughly one shape and moving in a single direction. And that's kind of what, if we look from the start here, that's kind of what these end up doing. Is that pretty clear? Do you all have a pretty good idea how three-zone swarming works by this point? I feel like I had some other examples in mind, and I thought, well, that might be overkill, and they might kind of get bored with that. So that's kind of the end of my examples for three-zone swarming, but I can answer questions if you have questions. But so just to recap, what's nice about this? At least as far as I've described it, we're going to be modifying it, but at least as far as I've described it, it's a relatively simple algorithm. Now, each agent just has to know the position and orientation of the other agents. Another really nice thing about this has a small dimensional parameter space. What do I mean by that? Well, when I'm thinking about using artificial intelligence, or what we used to call computational intelligence, which was kind of like a simpler version of artificial intelligence, just we had sort of more modest goals. One of the things that we were always looking at is a small dimensional parameter space. So that is to say, if I have an algorithm that has certain parameters, I want to make sure that there aren't too many parameters that the algorithm is modifying, because then I could get a chaotic system. That is, I could get a system where a small change now could make a great change later. I want a system where if I make a small change on the input, it should have a small change on the output. And there are ways to make this precise. So one of the ways we might make this precise is by looking at, like, for a function, we might call a function Lipschitz if it never changes too much. We might say we have bounds on the derivatives. There are all sorts of very specific ways, depending on what it is that you want control on. But in particular, when I'm dealing with computers, man, I'm no longer guaranteed anything's continuous. I could flip one bit and then have the output completely change. So a small dimensional parameter space says I only have a few parameters, And what I'm hoping is not only is this parameter space small, but I also hope that a small change in a parameter will have a small change in behavior. So why is this a small dimensional parameter space? Well, if we think about the three-zone swarming model, it just has two distances and then the relative weights of those distances. So remember I said about the high priority, medium priority, low priority. So I could weight those. Instead of just saying do this, if not, then do this, if not, then do this, I could actually just give them weights. I could say, okay, here's your repulsion direction, and here's how much you want to repel. Here's your orientation direction, and here's how much you want to orient. And then here's your attraction direction, and here's how much you want to attract. And that can deal with cases when maybe I've got an agent that's just on the edge, and it sort of starts to get away from the group and then go back to the group and go away from the group. And that sort of oscillatory behavior can be annoying for various applications. So that behavior where things are sort of wiggling back and forth as opposed to just staying put and moving, or staying put relative to one another and translating. So this small dimensional parameter space is very, very useful for us. And as you'll see when we modify it. Adjusting these parameters can lead toward sort of the things that we expect swarms to do. Like I said, translating, and that's just sort of taking a formation and moving in a direction, but also milling. So how many of you have been to an aquarium and seen fish just go around in a circle? So we call this milling because this big, almost like a donut made out of, hundreds of fish is just spinning around and around. We call it milling because it looks like a millstone, which is what they used to use to grind up various grains. It's a giant stone shaped like a donut, and they would use it to grind up grains to make bread. So this three-zone swarming model, I think, is very powerful. A lot of people think it's very powerful because it's got a simple set of parameters, but small variations in that simple set of parameters can lead to a lot of the expected behavior we see in nature. Okay, so now I'm going to shift gears and I want to talk about signal reconstruction. So we'll get back to swarming in a minute, but does anybody have any basic swarming questions, like from the background? Okay, and if you have questions, feel free to write them, even if it's a couple minutes late. I'll get to it as soon as I can. Okay, so now totally separate thing, which is signal reconstruction. So we're gonna kind of forget about the swarming for a minute, and let's just suppose that like I'm on the phone, and I'm talking on the phone. I'm on a train, and then the train goes through the tunnel, and while the train's in the tunnel, I can still kind of hear the person, but it sounds kind of echoey or reverby. So what's going on there? Well, the way that our voices work, the way that we use spoken language, we tend to have long tones, and those tones come from parts of words. So that's where we have the vowels. And then there are maybe short starts and stops to those, but those long tones, if those get chopped up, that sounds funny. So what a telephone will do is if it doesn't have any data, it'll just repeat the data that it had, and that'll oftentimes be a pretty good approximation. Like if you heard every other sample from me speaking, you could probably still figure out what I'm saying. So when I'm trying to reconstruct a signal, what I'm thinking is I have some signal, which you can think of as a function here. This is a function from the interval between -1 and 1 to the real numbers. And I'm only getting some of the information of that function. So there's this nice smooth curve, and I'm only going to be picking up pieces of this smooth curve. Now we're going to assume that this function is well behaved. So I'm going to assume that it's maybe continuous. Maybe I'll assume that it's Lipschitz. Maybe I'll assume that it's in some Sobolev space. Whatever, man. All sorts of assumptions we can make, but let's just assume I've got a well-behaved function. Now, given a few values of f, how closely can we approximate f? Now, again, if this function was not well behaved, then there's no guarantee, right? My function could just be a set of random numbers, and this data point says nothing about any of the other data points. But if my function is well behaved, that it, if it's like continuous, or I know how quickly it can change, then knowing this data point actually tells me something about what's nearby. And one of the big problems in this signal reconstruction, one of the big pieces of the signal reconstruction problem is, where should we get these samples from? Now, there's something sort of hidden in this opening statement. I'm assuming that I know the start and the end of my signal. Okay, this is a big assumption. When I'm on a telephone call, the telephone doesn't know, I guess it knows when I started, but it doesn't know how long I'm going to talk for. So it has a different problem to solve. Here, I'm assuming that I know the beginning and the end, and I want to find the best way to reconstruct what's in the middle. Okay, so I want to kind of argue this to you without getting too technical, but if we're talking on the telephone, or does anyone use a digital audio workstation to make music, like Reaper or FL Studio or something? Or does anybody listen to WAV files on your computer? You might, if you're listening to music on your computer and you see .wav, there's going to be some sample rate associated to that. So there's going to be, this is some, sort of, we're approximating the position of the magnet on your speaker at these points in time, and approximating that closely enough gives us kind of a wave. Well, that is going to be a uniform distribution. That's going to be, let's take, in the case of a standard wave file, 44,000 times per second, we're going to take a snapshot of where that pressure wave is. And that's going to give us a pretty good reconstruction for human audio information. Can anyone tell me why we sample it at 44,000 times per second, or 44.1 thousand times per second for human audio? Any guesses? No reason you should know this. I'm just curious if anyone's got a guess.
For it to be listened. So
yeah, recording to be listened. Yeah. Why would 44,000 be such a nice number?
Because it's a lot.
That's a really good point. It is a lot. It's a lot, and 44,000 is more than 2 times 20,000. And when I'm emphasizing human audio, humans typically can't hear anything higher than 20,000 cycles per second. So if something is oscillating back and forth more than 20,000 times in a second, our ears can't pick it up. So how can I tell if something is going up and down? I need to get at least 2 pictures of it. Otherwise, when you see like a movie where the helicopter blades are just staying put, or like the wheels on a car look like they're not moving, it's because whatever is rotating at some multiple of the speed of the frame rate that you're watching this film on. So 44,000 is conveniently more than 2 times the highest frequency we can hear. So if we sample at 44,000 hertz, we'll for sure be able to pick up any oscillation that humans can hear. Okay, I'm slightly lying, but that's sort of the idea. But remember, like I said, here we're operating on a closed interval. So now we can actually do better than this uniform sampling. So what's this second thing that I said here? Edge biased. Okay, what's going on with this uniform distribution? If this point is kind of telling me some information about the whole area around it, and this point is kind of telling me some information about the area around it, then these 2 points are kind of both covering the middle. And these 2 points are kind of both covering this part. So why would I want more about the edges? Well, really, there's only one point kind of listening in to the edge. So we want the points to be a little bit closer to the edges. But now if I edge bias too much, that is, if I put things too close to my endpoints, then I'm going to miss out on what's happening in the middle. So what is a really nice balance between edge biased and uniform? We want something in between. Something in between that happens to be sort of mathematically optimal for most applications is the zeros of the Chebyshev polynomial. Now, if you've seen this name before, it's probably because Chebyshev did a whole bunch of awesome mathematics, and this is yet another piece of awesome mathematics named for Chebyshev. So I'm not going to go too much into the details of this, but I want to show you some information so you have some background on the Chebyshev polynomial. So here's a definition of the Chebyshev polynomial. So t sub 0, or the 0th Chebyshev polynomial, is just 1. So look at that. If you can imagine a function f of x equals 1, you have just imagined yourself the 0th Chebyshev polynomial. Congratulations. Okay, the first Chebyshev polynomial, t sub 1 of x, is the polynomial f of x equals x. Hey, look at that. You now know 2 different Chebyshev polynomials. That's probably going to be about enough to figure out the rest. Okay, and then this one gets a little bit hairier. So the Chebyshev polynomial numbered n plus 1 is equal to 2x times the nth one minus the n minus 1th one. So like the Chebyshev polynomial t sub 2 of x is going to be 2x times t sub 1, so that'd be 2x squared, minus the one before that, so 2x squared minus 1. Now, equivalently, we can define Tn of x as cosine of n times cosine inverse of x. Now, if you know what this means, that's great. If you don't, that's fine. We don't actually need to know what this means. I'm just giving you a little bit of background in this. Now, why are we so excited about the Chebyshev polynomial? It gives us this pointwise error. So let me break this expression down for you a little bit. So if I know that I'm sampling, like I'm taking the maximum over t between plus and minus 1, so absolute value of t is bounded above by 1, then I've got the absolute value of the n plus first derivative of f evaluated at any point over 2 to the n times n plus 1 factorial if I'm sampling at the zeros of the nth Chebyshev polynomial. So what does all that mean? If I take this formula and compute the Chebyshev polynomial of index n, and I find the zeros of that polynomial, and I sample some function f between plus and minus 1, the error, when I go to reconstruct it, is bounded above by this. Now, what's nice about this expression? Let's try to understand it. Okay, on the top, so the error. What makes this error big? On the top, if the top gets big, that means if the n plus first derivative of f is big. So if the function that I'm trying to sample has really steep ups and downs, then I could have a big error. But the more and more Chebyshev polynomials that I look at, the smaller my error gets. Look, I've got n plus 1 factorial. Do y'all know factorial? This means n plus 1 times n minus 1 times n minus 2, all the way down to 1. And I've also got a factor of 2 to the n, which means as n is large, this error is getting really small. Okay, so here is a picture of a Chebyshev polynomial. I picked the 15th Chebyshev polynomial, plotted it between plus and minus 1. Okay, you got a wiggly line. What do I care about with this wiggly line? Let's look at the zeros of this Chebyshev polynomial. And I want you to appreciate they are clumped up near the edges, but then they spread out towards the middle. However, there's still some representation in the middle, right? So they are getting, they're grouping up their higher concentration near the edges, but in the middle, there's still somebody there. So if we go back to these extremes, it's not too uniform, and it's also not too edge biased. It's something nice and in between. So these are the zeros of the Chebyshev polynomial. Okay, the expression I gave you here just says, yeah, we've got a really nice error, but you don't have to really parse in all those symbols if you don't want to. Just, we want some way of having things sort of clumped near the boundaries, but also represented in the center. Is that fairly clear? Like the basic idea there fairly clear? Okay. So what I want to do now is I want to interpolate some field of values in an area. So now it's no longer just a one-dimensional function. I'm thinking of this as a two-dimensional function in an area, and it's modeled by a function, f taking R2 to R. So I guess, how many of you understand what I mean when I say f takes R2 to R? I guess, have you all seen this expression before? Do you know what this means? I had a similar expression earlier. I'm just sort of scanning your faces to see if there are nods yes, or thumbs down, or if anyone's crying or sleeping, so I can have some idea. So I'm seeing some nods no. I appreciate the feedback. Okay, so since I wasn't sure, I got some examples of functions that go from R2 to R. So what is R? When I write R like this, I mean the real numbers. So, 1, 2, 3, 4, 5, those are natural numbers. -1, -2, those are negative numbers. So, the natural numbers and their negatives, and 0 is the integers. Okay, what are real numbers? Those are all the fractions in between and all of the transcendentals and other things in between the fractions, all the irrational numbers like square root of 2. Those are the real numbers. So any number you can imagine with no complex part is probably a real number. So what is R2? Well, if R is the real numbers, you can think of the real number line. R2 is then the XY plane. So it's the real number line and the real number line, and we're looking at pairs of real numbers. So if I want to interpolate a field of values in an area, I've got a two-dimensional space, a big two-dimensional space, and then I've got a function that takes all of those points as inputs and spits some function out as an output, or sorry, some number, real number out as an output. So here's an example. And this example is going to be carrying us through for quite a while. F could take, say, the latitude and longitude of a point on the Earth as inputs, and then it could output the temperature. So when you all look at a weather map, you're actually looking at a function that's taking values from R2 and giving you values in R. So there's an example like this. Anytime you look at a weather map and you see like, oh, it's like 25 degrees here, and then out here it's only 20 degrees, and then, oh man, out here it's nice and temperate. It's 15 degrees, right? So when I'm talking about F taking R2 to R, I'm thinking about two-dimensional input, one-dimensional output. Now I'm going to make a simple assumption, an assumption to simplify things, and we'll see some sort of diagrams that'll hopefully reinforce this. I'm going to define the boundary of a field to be the level curve where F is less than some threshold value. So what does that mean? Imagine that I'm looking at this weather map again, and I only want to see, I really want to focus on the area where it's, super hot. So, you'll see them draw these curvy lines around the areas where it's above, say, 15 degrees Celsius and below 20 degrees Celsius, and then between 20 and 25 degrees Celsius, and then between 25 and 30 degrees Celsius. And those are all these different regions. What I'm going to do is I'm going to say, well, okay, but outside of a certain area, I don't care about the function anymore. So if it's below 15 degrees Celsius, I just don't care. It's not hot enough for me to be worried. So if I'm thinking about not a weather map, but if I'm thinking about a forest fire, I want to figure out where this fire is the hottest. Where is it 100 degrees Celsius? Where is it 150 degrees Celsius? Where is it really, really hot? Actually, I don't know how hot forest fires get, so I don't know if those are even reasonable numbers. But you can still imagine, maybe if I'm looking at sort of a weather map of the forest fire, I'm not concerned about places where the temperature is lower than the temperature of fire, because that stuff is not on fire, right? So I'm going to view the boundary as the places that are not on fire. So let's see an example. So you can imagine this is, a map of some region, and here the yellow is low temperature but still burning. Here the orange is medium temperature but hotter than low temperature, but not super, super hot. And these red regions are very hot regions. Now, I've just to make it easier for our eyes to see, I've drawn this as a discontinuous function. So it goes from hot to medium to low temperature fire. And then outside this white area is where there's no fire. In practice, this would probably be more of a smooth curve. Moreover, it would be changing in time. And we'll get to the changing in time in a minute. But what I want you to think about right now is this picture of sort of here is where the forest fire is, and here's the boundary of the forest fire. So outside of this curving line, nothing is burning. Out here, stuff's not on fire yet. So I'm trying to fight this forest fire, and I think, okay, what's the most important thing? Do I need to cut trees down around here so that the fire can't spread? Or what if we just dumped water on these two hot spots? Then maybe it would cool off and burn itself down. I don't know what to do because I'm not inside the forest fire, and I don't want to go inside the forest fire because I like not being on fire. I like not burning, right? For whatever reason. Okay. So what does this have to do with a field reconstruction? Because, I spent all this time looking at the zeros of this Chebyshev polynomial. I gave you all of these icky math expressions. And then we had these pictures of something is too uniform, too edge biased. Well, what I want to do is I want to get this picture without putting myself in danger. So I'm going to put my robot swarm into the fire. Why? Because I hope my robot swarm gets back, but like if a drone gets melted, that's one thing. If a person gets melted, that's quite another, right? I don't mind if some equipment gets damaged, but I do mind if a person gets hurt, right? So I don't want people to get hurt. And again, I'm going with the forest fire model here, but this could be again toxic waste in a nuclear disaster. This could be an oil spill. This could be a chemical plume where like a factory has exploded, or a train has come off the tracks and there's some dangerous chemicals. This could be we're looking at runoff from a factory farm. There are all sorts of applications of this. You could be looking at concentration of chemicals in the bloodstream for all I know. Anyway, so just with this general idea of forest fire, I feel like it's big enough and small enough that we can think about it. And of course, all sorts of stuff that you could do in space. So now, how do I tell what the temperature is? Like there's no, or maybe there's a rough weather station, but it's not like I can turn on the Weather Channel and just look at, precisely which square meters are burning the hottest. So I'm going to send my swarm in there. Now, the question is, where should the swarm bots go? So I want to show you an example of just a small swarm, or sorry, several examples of a small swarm trying to sense this fire, and what could go well and what could go wrong. Okay, so let's look. So I'm going to show you several pictures of just samples from the swarm. So if my swarm is nice and spread out, I might see like, the fire is not super hot in some places. It is super hot in other places, and it's sort of medium over here. Now, I would probably want more than 6 robots to figure out how hot this fire was, and I would probably want them, moreover, to fly over and be sending me data back continuously. But just for the moment, you can see some different pieces of data here. Okay, so I'm going to say that that's for 6 robots, that's a reasonable distribution of robots. But now let's look at maybe some poor distributions. What if all my robots just feel like getting into a line? Then they might say, look, the fire is uniformly sort of medium. It's not too cool, it's not too hot, it's just sort of medium. All right. So maybe I put all my robots in a line and they tell me, yeah, it's just medium. What if I do this? What if I just happen to get I happen to put the robots in little clumps and they happen to get to the hottest spots? As far as I know, this whole black rectangle is the hottest fire you've ever seen from this data, right? If this is all the data that I have, as far as I know, the whole thing is the hottest fire possible. Everything's going to be just completely gone. Just there's going to be no more earth left. So between these three different distributions, you can see some are better, some are worse. Now let's look at this last one. Here, these are nice and spread out, but it's sort of maybe bad luck or whatever. It says, oh, the fire is almost burnt out. You see, it's not very hot. I guess we're okay here. So while here we have a picture of the whole fire and we can sort of imagine, oh yeah, I know I need to send water to the two hot spots. I need to send a helicopter to dump water here and helicopter to dump water here, and then we're going to be okay. But just standing on the ground and not being able to see that, I send my robots in and they say, they tell me this, or they tell me that, or they tell me the other thing, or they tell me this. Now, if I put all those pieces together, I might be able to get a rough approximation of this picture. But do you see how just choosing sample points, just choosing the places where I'm sensing the fire is already kind of a difficult question? Okay, this is already kind of a difficult problem. Now you might, one easy answer is we'll just get more robots. Sure, but that's very expensive and we only have so much money to fight this fire, right? Is this fairly clear what's going on so far? I guess I would just ask for head nods or thumbs up, thumbs down. I feel like it's pretty clear. Okay, I'm getting some head nods. All right, awesome. So fairly clear. Okay, so we can move on. So and again, if I ever move on and you still have questions, just chat me something. Say, wait a minute, I still don't understand this. So what I'm really trying to do now is I want to approximate that field. I want to approximate that two-dimensional area with the varying outputs. You can think of that as three-dimensional data if you want to, but I want to somehow approximate that with a relatively small number of sample points. So again, in the back of your mind, at the moment, this is just a math problem, but at the back of your mind, think, these are mobile robots. These are robots that are going around sensing. So I'm flying my drones through, and they have temperature sensors, and they can send me that temperature data. So where do I want the drones to go? Like I don't want them to all clump up too tight. I also don't want them to get into some weird formation where they might give me biased data. So I want to figure out roughly what this fire looks like by taking a small number of sample points. So back to what I called that boundary, I want the sensors to stay within a region of interest. So again, back to this picture, I don't want the sensors flying over here where there's no fire. I mean, sure, get to the boundary, verify there's no fire, but then go back in, right? I can walk around and see that it's not burning here. I want data in the zone of interest. I want data where I can't go. So as these temperature sensors are flying out and they see that the temperature is getting low, I'm gonna want them to stop here. I don't want them to get outside of the yellow area. Okay, that is determined by some threshold value. So there's some temperature value, and I say, hey, if you get below this temperature value, get back in. Okay. Now here's where I'm going to start waving my hands. So something that I want you to understand about science in general is when you're reading science in a science textbook, it's often been, so many people have done so many things to verify it and boil it down and simplify it and make sure that everything makes sense, that it's this very simple, clean, tidy package. Like, you learn these things like water boils at 100 degrees Celsius, that took a lot of work to determine, right? Before we had a solid temperature scale like Celsius, before we had really precise ways of heating water, it was just like, oh, it's on the fire, the cauldron's on the fire, now it's bubbling. The cauldron's off the fire, now it's not bubbling. I don't know. So this whole of science is a very rough and messy thing. So what I've told you is I've told you something about robot swarms, and I've told you something about the zeros of a Chebyshev polynomial. And now I'm going to do that rough science thing, which is to kind of put them together, but it's going to be a big mess. Okay. It's not going to be perfect. And that's something that I want you to understand about science in general. When we're making new science, it's rarely this clean, tidy package. It's rarely this thing that that just oh, okay. No, I see your question. I'll get to that in just a second. So just science in general, when you're working on a new experiment, it's rarely like, red, red and blue make purple. It's rarely something so clean. It's more like, well, some of the time this kind of works and some of the time it kind of doesn't. And that's why if you, if you read science articles, they'll often use phrases like, oh, well, this polymer, our data suggests that this polymer may have an effect on that growth or whatever. So they'll often use the word suggest because they're not certain. So what we're going to do here is going to be very messy and very uncertain, but I want to take those two pieces and put them together. So here's a question. So why can't we just expect all the fire is as hot as possible? So you might, right? And that is what we would call a first order approximation. So if you don't have mobile robots and you're trying to fight a fire, you can just assume it's all as hot as possible. And that is a great first approximation. But now let's suppose that you only have so much water. And so if I assume that all the fire is hot as possible, I'm just going to dump that water right in front of me and hope for the best. But maybe with just this quantity of water, I could put the fire out if I knew the hottest points. And again, I'm not an expert in firefighting, but just something where there's a field with varying values. So the forest fire is a nice example because it's got hot places and cooler places. But if I maybe can allocate my resources more efficiently, then maybe I can save more of the forest and keep it from burning. So then we have a comment. There's much more things that are hotter than fire. How do you expect we would represent the other temperatures? The others is temperature. Oh, right. So yeah, suppose that there's a forest fire on top of a volcano with lightning strikes and also, some sort of like fire spell happening. So yeah, you might need to calibrate your temperature sensors differently. Think about like when we have sent probes into space, sometimes they get so close to the sun, they need heat shields so that they can keep transmitting data back to us. And sometimes I think we've just sent them into the sun and we get data until they burn up. And that's how I think we would do this here. If there's a forest fire and it's close to a community, I don't care how many robots die as long as I can save some human lives, right? So we're thinking about maybe protecting these so they can detect high temperatures, but if they stop working, we can assume that it's an even hotter temperature. So this, if I understand your question correctly, Tang, you're saying like, how do we express this whole temperature scale? We would hopefully say, okay, here are the highest and lowest temperatures I expect to see, and to design those drones to fit within those temperature ranges. So it wouldn't be just a plastic quadcopter that you can, buy at the mall, right? It would be something sort of industrially built. These are great questions, by the way, and I very much appreciate them. So the big thing here is I've told you about this swarming technology, and I've told you about this Chebyshev polynomial, and now we're gonna smash them together, and it's I just want you to envision like a child playing with clay and going, like it's not going to be perfect. And that's one of the reasons I like speaking on this, because I like to show people that that science is not perfect. Like as we're doing science, as we're discovering new things, it's rarely this perfect, complete picture. Okay, so I've sort of alluded to this earlier, but I want to make sure that my sensors, that my drones can move quickly compared to the time it takes for the field to change. So I'm thinking of a quadcopter flying through a fire. Okay, fire gets hot and then it burns down. That might take some minutes or some hours for the temperature to go up or down, but hopefully a quadcopter can move in seconds, right? If I'm looking at an oil spill where maybe things are moving more slowly, then I don't need, you know, a quadcopter that can move, that can zip around. Maybe I can use like a slow submarine that uses low power. Again, in the back of our minds, we're always thinking about how much money are we spending? How many resources are we using? Because if this is just a fantasy world, then I can spend infinity dollars and have all of my quadcopters built out of titanium or, you know, whatever. But in real life, that's probably not the case. So I want to assume that I've got sensors that can move quickly compared to, you know, how the field values are changing, but maybe not too quickly. Okay, so they can't move instantaneously. It's not like a computer programming where a computer program where I'm just picking points on the screen. These are physical objects that are going to have to move. Now, something that I alluded to earlier, before when I was showing you the 3-zone swarming, I said, I'm going to say that every robot knows the position and orientation of every other robot. And I said earlier that that might not be the case. And so we're going to make this assumption that there's so many robots and they're spread out over so much of a large space that they can only communicate with the robots close to them. Now, just the problem of what we call communication collisions is really hard. So you think about when you have a whole bunch of people using their cell phones at the same time in the same area, maybe your Wi-Fi gets spotty. You imagine a bunch of robots doing this. Can you imagine thousands of robots all packed in a tiny space? So we're going to assume that they can't always communicate with each other. That's going to be a fundamental assumption in our simulation that I didn't really talk about too much here, but I hope you can appreciate that if I don't have that every robot knows exactly where every other robot is, this could get a lot more complicated. Now, one of the good things about that, like I mentioned earlier, that's pretty computationally expensive if every robot is computing its direction to every other robot. Now, if I'm only computing and communicating my direction to the nearby robots, then that is going to be less computationally expensive. Because you imagine if your robot's flying, it's got to make decisions quickly. It can't be sitting there doing trigonometry and waiting for, you know, a Raspberry Pi to crunch through, you know, a system of 1,000 equations and figure out the best path forward, right? It needs to be quick. It needs to be a simple algorithm. So assuming that we don't have good communication is a bad thing, but it also can simplify the algorithm, okay? So here is a sort of a drawn example of an approximate Chebyshev distribution. And this is what we called our work. We called this an approximate Chebyshev distribution, because it's not actually the zeros of a Chebyshev polynomial, because at least I don't know of a good 2-dimensional or 3-dimensional zeros of a Chebyshev polynomial, because it's just a fundamentally different problem. Now somebody might say like, oh, well, there's the following generalization of Chebyshev to higher dimensions. That might be a thing that someone can do. But as far as how do we get zeros from that are points and not zero level sets, that could be a complicated problem. And that's actually something that somebody might want to study at some point. But for us, what we're saying is, loosely speaking, if I slice my swarm, so I'm imagining, you know, hundreds of robots here, or at least dozens of robots. If I look along any line, I should have sort of a Chebyshev distribution. So I should have some, you know, a few robots near the center, but robots should be clumping up near the boundaries. So if you sort of cover up the top and cover up the bottom and just look along this horizontal line, these are hopefully distributed somewhat like the zeros of the appropriate Chebyshev polynomial. So it's not exactly symmetric, like this one's a little closer to the center than this one is, but at least in general, near the boundary, robots are closer together, and near the center, they're hopefully not as close. Now, something that you might notice, since we have this concavity here, since we have this place where the boundary gets closer to the center, robots are clumping up even more along this line than they are along, say, this line. And so this is, again, owing to this approximate Chebyshev distribution, because we don't have an exactly symmetric field. You know, I don't know how a forest fire is going to burn. It might not be an exact perfect circle, right? So, oh, I got a question. plus, plus, plus. Oh, I think somebody's maybe leaning on the keyboard by accident. Okay, so what we're going to try to do is take our 3-zone swarming algorithm and somehow modify it to get this emergent behavior. Do you remember at the beginning where I said, I want an emergent behavior? I want something like this to come from very simple rules applied to a whole bunch of simple autonomous mobile robots. So, like I said, we're going to modify the 3-zone swarming algorithm, but we're going to incorporate forces based on boundary proximity. So as robots get close to the boundary, there's going to be a little bit more weight put on some other factor in the decisions on where it moves. Remember with the 3-zone swarming, it was just move away from people that are too close, move like people that are medium distance, and move toward people that are far away. Now we're going to have kind of a fourth rule, which is also obey something to do with the boundary. And this boundary thing is going to take a minute to explain. So the fourth rule is a lot more complicated. Okay, so how does it know when it's on the boundary? What we're going to do is we're going to add in a force that it's going to want to go towards higher field values. Again, if we continue with the temperature analogy, we're going to say we want it to stay closer to higher temperature. Now, if an agent has somewhere a 90-degree field of view, so if it can find a right angle in its field of vision where it sees no other robots, then it's going to say, guess what? I am an edge node. It's going to say, I am on the boundary or close enough to the boundary. So it might not be exactly on the boundary, but it's going to flip a switch in its mind that says, ooh, I'm a boundary member. And if it's a boundary member, it's going to behave a little differently. Now, boundary members are going to be on the edge. They're going to be on the boundary. And then robots that are close to robots that are on the boundary are going to be given what we call an edge depth. So someone on the boundary has an edge depth of 0, whereas someone next to someone on the boundary has an edge depth of 1. And then someone next to them would have an edge depth of 2. Now, this gets into a really complicated graph theory algorithm. I'm not going to go through that carefully because I want to keep this whole presentation to 90 minutes. And going through the whole graph theory algorithm, I think would just take us a little too far afield. It's really interesting. It's really fun. And if you want it, I can give Tung the paper and you can read about it carefully. But for now, I'm just going to show you a couple of pictures. Okay. So, sorry. And it also needs to know something about its proximity to the center. Okay. So here is what I've called an approximate Chebyshev swarm. And it's that same fire outline. So if we, let's see if I can go all the way back. So, I'm working with this same fire outline. I'm working with the same fire example, even though this should work for other types of problems. So even though it's hotter in some places, cooler in some places, we're going to forget about that for the swarming. We're just going to say it's either above my threshold or below my threshold. Either I'm flying around something that's on fire or I'm not. So if one of my swarm members gets outside of the fire, gets to where things are not on fire, it's going to say, oh, I'm not doing anybody any good here. It's just, okay, it's not on fire, and it's going to fly back into the fire. So these are, hopefully sort of going into the fire, out of the fire, into the fire, out of the fire. And what do they notice? Well, these are going to identify themselves as edge nodes because like each one of these has somewhere a 90-degree view with no other agents. See how this one right here, if it looks out this way, and so it's probably not going to look, but it'll probably have location data. And if it knows locations that there are no other nodes in this 90-degree range, then it says I'm an edge node. So let's look at this node, for example. This one is not an edge node because no matter where, let's see if I can draw on this. No matter where I draw a right angle, there's an edge node, there's another node here. So this right angle doesn't work. What if I did, like this right angle? Oh, there's an edge node here. That there's another node here. So this is not an edge node, right? So essentially what I'm saying is this one's not going to be an edge node. This one is going to be an edge node. And if I run all the way along the boundary, we'll see that each of these are going to be edge nodes. This one's not on the boundary, but it is an edge node because there's a 90-degree view here. So edge nodes, I'm going to say, are going to have an edge depth of 0. They're on the edge. Then you notice this one is a closest neighbor to this node. So it has an edge depth of 1, right? These two, okay, they are close to this one. So they're going to have an edge depth of 2. Now you might say, well, wait a minute. Why doesn't this one just say that's its closest neighbor, or maybe like that's its closest neighbor? Again, this is a complicated algorithm. It's not that hard, but what we're going to have these nodes do is look at all the depth 0 nodes, then all the nodes that are closest to them have depth 1. All the nodes that are closest to them have depth 2. So a node might think, oh my goodness, I'm depth 4, but then another agent becomes an edge node and says, oh, actually, instead of taking this path to the edge, this is a shorter path to the edge. So depending on the distance to the edge, they're going to use this threshold as a force to push it closer and closer to what we call the center. Now, this is a sort of a blobby thing, but it's one thing. You can imagine this might get complicated if I had 2 separate forest fires. Maybe I have a forest fire and the middle stops burning and then it turns into 2 separate forest fires. So this can be a really complicated scenario. This can be a very dynamic scenario, but this is the basic idea. Now, depending on how far a node is from the edge, it's going to behave differently. So we have edge nodes, and edge nodes identify themselves as A, being inside the fire, and B, having a 90-degree field of vision where they don't see any other nodes, and then other nodes organize themselves accordingly. And so the higher your distance is from the boundary, the more you're going to want to be away from other agents. And why is that? Because again, we have an approximate Chebyshev. We want to make sure that whatever distance robots are from each other near the boundary is closer than the distance between robots when they're close to the center. But we still want some representation in the center. So by tweaking those weights, remember how I said we've got a small parameter space? We have a small number of sort of dials that we can turn on our machine. We can make this behave to where the distribution, that is how dense they are, it gets denser closer to the edges and less dense in the center. So I explained about the 3-zone swarming, I think pretty carefully. I explained about the field reconstruction and why we wanted to use the zeros of the Chebyshev polynomial, I think fairly carefully. But you may have noticed that this got a lot fuzzier and a lot messier, and I started skipping the details a lot more. And I really want you to understand that, yes, it's complicated, so I'm skipping some details, but also science is messy. Doing experiments is messy, even though all of this was done on various computers, so that we didn't actually set anything on fire. We didn't actually burn up any quadcopters. This is all a very messy thing. We did the best we could, and I'm going to show you some hard data that we have available in our paper. But this is a messy thing, okay? So here is sort of the big finish. This is, I'm going to show you some QualNet simulations. So what is a QualNet simulation? Well, QualNet, at least it used to be the industry standard for mobile robot simulations. QualNet is going to be a high precision computer simulation. So you can imagine just like, it's just running the positions of all of these robots, but it's going to simulate not only their locations in physical space, but it's going to simulate, remember I told you about those communication collisions. So it's going to simulate the bandwidths that these robots are communicating with each other with. And if those bandwidths get overlapped and the communication gets garbled and the messages get lost, and maybe they bump into each other. It's going to let all of that happen in the simulation. So this is a very powerful simulation that saves us from having to spend millions of dollars on thousands of little robots. So basically, we ran a bunch of simulations. So we put this computer code into a giant supercomputer and let it run for hours and hours and hours. And it gave us a whole bunch of data. And I used, so that this, I made this picture in MATLAB, which you may have heard of. So this, as you can see, is not that pretty of a picture, but I want you to appreciate this is, millions of pieces of data that, ran on a supercomputer for hours and hours and hours. It was the kind of thing where you just kind of like hit go and then leave for the weekend and come back on Monday and hope that it didn't say syntax error. We churned all this data and then just presented, after a certain runtime, the final locations of our robots. And then we have what we call the maximum error. So we're imagining that we have a function that's on, supported on the square. So it's zero outside of this square and it's non-zero on the square. And we put these swarm robots on it, and then we pretended those swarm robots sort of took the temperature, or they took samples of that field, and then they reconstructed it using what we call radial basis functions. So remember how I said that a sample sees not only where it is, but if the function is continuous, that tells me something about what's happening nearby. Think about my robot flying through a forest fire. If I know the temperature here, well, probably I know something about the temperature close to me, just maybe not so much about the temperature far away. So we had our swarm reconstruct this signal or reconstruct this field, and this is going to be the error. So the little circles are the final locations of the robots, and the color is going to be how much error. So where we have yellow, we're going to say pretty good reconstruction. Where we have green into blue, it's having some errors. And then wherever we get purple or red, we're having huge errors. Okay, so what I'm going to show you is a uniform swarm versus an approximate Chebyshev swarm. So remember when we first started talking about sampling or trying to reconstruct a function, we said, well, it seems like you might just want to, sample things regularly, just uniformly. That's how we do wave files. That's how I listen to music, So uniform swarm seems like not a bad idea. Now, obviously, this isn't uniform throughout the entire space. We've included that threshold value. So this is a uniform swarm, but modified with the threshold. So you can see this robot has hopped out, but we just took a snapshot. So probably if we waited another few time steps, it would come back in, right? So I want you to just look at this, and we've got numbers and we've got hard data, but I want you to look at this and see like, okay, most of the square is pretty yellow. How would you describe where it's not yellow? You don't have to say it out. You can just think of it in your head, but I want you to think, how would you describe where is this not yellow? You can answer, you can unmute and say it out loud, you can type in the chat, or you can just think about it. All right, something that I notice is that we have errors near the corner, right? Every time there's a corner, we have some errors. Why do we think that might be? So if a boundary point here is a boundary in one dimension, a corner is a boundary in two dimensions. And you remember how we said the uniform sampling in one dimension really had problems near the boundaries, which is why with our approximate Chebyshev, we wanted to stack things up a little bit more near the boundaries. So a corner is not only a boundary, it's kind of a double boundary. It's like worse than a regular boundary. Moreover, there are these sort of disturbances that form like a green X. Do you all see these sort of green X disturbances? Okay, so that's the uniform. swarm. So now we have our approximate Chebyshev swarm, and we hope, we did all this work. I've been talking to you for an hour and 25 minutes. You hope that that would somehow outperform the uniform swarm. And it maybe kind of did. Okay. What do we see here? It's still pretty much yellow in the middle, and we have some errors on the corners. Now I'm going to say that the corner errors are not as bad here and here, and they never get red. So our worst errors aren't as bad as the worst errors here, because we have some purple and red here, but we do have significant errors. Now in the paper you can see the data aggregated and worked out, but I'm just going to say, looking at these two qualitatively, maybe better, but was it worth an hour and 25 minutes of your time for I don't know. Okay, it's okay. I do want you to notice that these are more concentrated near the boundary and they're more spread out near the center. So this is at least achieving, in my mind, the goal of this approximate Chebyshev thing. Okay, so now what if we take some sort of a blob? So we have this blobby region, and we now had the uniform swarm, sample it, mill around, and then we took a snapshot. What do I notice? This uniform swarm really kind of seemed to have trouble conforming to the blob. See how there's all these agents that are outside? And we have one really big error here. We have some errors here. But again, notice that the error is concentrated at the boundary, and in the middle, we're pretty much okay. So let's look at the approximate blob. That should be way better, right? Well, actually, looks like it's kind of worse on the inside, right? This is pretty much yellow all the way across, whereas this is yellow with some green. We had, even with this approximate Chebyshev thing, we kind of had some of our agents popping out here. I don't know if it's better or worse. Just looking at the picture, I don't know if it's better or worse. Again, the uniform got some red, whereas the approximate Chebyshev did not. So the maximum error was definitely better. But I don't know. Again, it's a little better, but maybe not a lot better. I'm not sure. So final comparison. Okay, let's look at this uniform circle. And again, we did a whole bunch of simulations. This isn't it. I've just picked a few to show you sort of places where we did well, places where we didn't do so well. But now here's where we really knocked it out of the park. Okay, so if we just have our data represented on a circle, and we also ran this with different numbers of robots, different types of fields, all sorts of things. Here, look at all this error near the boundary. Look at all these red and purple and blue regions. And even a little bit backed away, we're having, oh my gosh, we got all this error versus, yeah. Look at this. There's a tiny bit of red here, a tiny bit of purple here. Other than that, we've got this nice, clean green, right? Compare all this purple and red, all that dark blue to this. There are definitely some blue spots. We definitely have some error. But again, this is using fewer robots. But it's way better than that. And moreover, we can quantify this. So if you're interested and you want to read this math paper, which I'm not saying anybody ever should, but we write down precisely what happened after all these simulations. So with that, I want to thank you so much for listening to me talk about approximate Chebyshev field reconstruction using mobile robot sensor swarms. And I want to say thanks. So with that,